You have a morning routine, maybe coffee, maybe a window you look out of while the day starts. The sun is there, the same sun it always is, sitting roughly 93 million miles away, doing what it has always done, giving light, giving warmth, making the whole system run. You do not think about it much, neither does anyone else. That is the point. There is something almost arrogant about the way we treat the sun. Not consciously, we are not rude about it, but structurally. We have built a civilization that depends entirely on it staying calm, and then we just assumed it would. Power grids, satellites, GPS, internet cables routed under oceans, financial systems running on timestamps synchronized to atomic clocks. All of it resting on the quiet assumption that the star at the center of our solar system is going to behave itself today. It usually does, but here's the thing. The sun is not a steady flame. It is a churning, magnetic, violent plasma engine roughly 1.3 million times the volume of Earth. At its core, the temperature is about 27 million degrees Fahrenheit. On any given day, it is releasing energy equivalent to billions of nuclear explosions per second. What we see from the ground, that warm yellow disk, is the surface. It is the polite part, the part the sun shows when it is in a good mood. It has not always been in a good mood. The scientific record, written in ice cores drilled from Greenland and Antarctica, in tree rings going back thousands of years, in the magnetized layers of ancient rock, tells a different story than the one we tell ourselves. A story of a star that has, on multiple occasions, I sent something so large and so fast at this planet that it rewrote the atmosphere, that knocked out the very systems that make life on the surface possible, that killed entire populations of organisms and drove others nearly to extinction, not in deep prehistory, not in the age of dinosaurs. Some of these events happened while humans were alive. One of them happened while people were having breakfast. In September of 1859, a British astronomer named Richard Carrington was sketching sunspots, a routine observation, when he saw something no one had ever documented before, a flash of intense white light erupting from the surface of the sun. He noted the time, he noted the location. He was looking directly at the moment of the largest solar storm ever recorded in human history. 17 hours later, it arrived. See, the entire telegraph network of the Northern Hemisphere failed, not slowed, not disrupted, failed. Some machines caught fire, operators reported receiving electric shocks. In Boston, telegraph operators disconnected their machines from their power supplies and found they could still send messages. The storm itself was generating enough current in the wires. The northern lights were visible from Cuba, from Rome, from Hawaii. People in the American Northeast thought cities to the south were on fire because the sky was so red. That was 1859, before power grids, before satellites, before the fiber optic lines and GPS receivers and data centers that run everything. Now ask yourself, what happens when it happens again? Because here is what the science actually says. The Carrington event was not a once-and-forever anomaly. It was not even particularly special by the standards of what the sun is capable of. Ice core data shows evidence of at least 2 solar proton events in the past 10,000 years that were significantly more powerful. One happened in 775 AD, another in 993 AD. Both left chemical fingerprints in ice on opposite ends of the planet, fingerprints so distinct that scientists were able to date them to within a single year. And those are just the ones we can read. The deeper you go into the geological record, the more events you find. Quiet extinctions, atmospheric disruptions, gaps in the fossil record that nobody fully understood until someone thought to look up. This is not a story about what might happen. It is a story about what already has, and what we have quietly forgotten. To understand what the sun actually does to a planet, you have to start with the magnetic field. Earth is wrapped in one. The geomagnetic field extends roughly 40,000 miles above the surface on the side facing the sun and stretches into a long tail, the magnetotail, millions of miles behind us, pressed outward by the solar wind. Think of it as a shield. Not a perfect one, but a shield. It deflects the constant stream of charged particles the sun breathes out, a flow of electrons and protons moving at roughly 1,000,000 miles per hour, and routes them around the planet. Without it, the solar wind would strip the atmosphere the same way it stripped Mars, slowly, completely. Over geological time, you would lose the oceans, you would lose the breathable air, you would lose the conditions that make anything alive possible. The shield works, most of the time, but the shield is not static. It bends, it compresses. And when the sun sends something significantly larger than its usual breath, a coronal mass ejection, a billion-ton cloud of magnetized plasma accelerated to millions of miles per hour, the shield does not break so much as it gets overwhelmed. The CME arrives, slams into the magnetosphere, and the field lines reconnect in a process called a geomagnetic storm. Currents that do not normally exist on the surface of the planet suddenly appear in the ground, in the wires, in the transformers that step electricity down to the voltage your home runs on. Here is what that actually means in numbers. A large geomagnetic storm can induce ground-level currents of thousands of amperes in power transmission lines. See, a standard high-voltage transformer, the kind that forms the backbone of a continental power grid, can absorb those currents for a few minutes before the core overheats and burns. These transformers are not off-the-shelf parts. Each one weighs up to 400 tons. Each one is custom-built. In the United States alone, there are roughly 2,000 high-voltage transformers supporting the grid. The global manufacturing capacity to replace them, if many failed simultaneously, is somewhere around 100 to 200 units per year. Do the math slowly, let it land. If a Carrington-scale event hit today and took out several hundred transformers across North America, the wait time for replacement parts would not be weeks, it would be years. Without power, water treatment plants fail. Without water treatment, municipal water systems fail within days. Our refrigeration stops. Fuel pumps stop. Hospital backup generators run on diesel, and diesel has to be delivered by trucks that run on fuel pumped at stations that run on power. The cascade does not take long to reach the point where the systems we have built to keep people alive begin to fail faster than we can repair them. A 2008 report by the National Academy of Sciences estimated that a Carrington-equivalent event could cause $1 to $2 trillion in damage in the first year in the United States alone, with a full recovery taking 4 to 10 years. The report noted that the social consequences, which are harder to model, would likely exceed the economic ones. That is one event, one storm, one bad afternoon on the sun. Now go back further. The 775 AD event captured in ice cores was not a geomagnetic storm. It was a solar proton event, a sudden burst of high-energy protons accelerated to near the speed of light by a solar flare or a coronal mass ejection of unusual intensity. The carbon-14 spike it left behind in tree rings around the world was roughly 20 times larger than anything produced by the Carrington event. Researchers who first detected it in 2012 described it as, at the time, inexplicable by any known solar mechanism. It took years of analysis to confirm what it was. A solar proton event of that scale does something that a geomagnetic storm does not. It penetrates the atmosphere. High-energy protons break apart nitrogen and oxygen molecules in the stratosphere, producing nitrogen oxides, compounds that catalytically destroy ozone. A large enough event does not just spike radiation at the poles. See, it creates a hole in the ozone layer large enough and deep enough to increase UV radiation at the surface for years. Crops fail. Phytoplankton, the base of the ocean food web, responsible for roughly half the oxygen produced on Earth, suffer mass die-offs. The effects move through the food chain with a slowness that makes them easy to misread. By the time civilizations feel the pressure, the cause is a decade old, and the sky looks completely normal. This may have happened before. There is a famine recorded in tree ring data around 536 AD, one of the worst in the Northern Hemisphere in the past 2,000 years, often attributed to a volcanic eruption. But some researchers have argued that the ozone depletion signature matches a pattern more consistent with a solar event than an eruption alone. The evidence is not conclusive, but it is not nothing. And then there is the deep past, the Lasham excursion approximately 41,000 years ago. Earth's magnetic field did not reverse, it weakened drastically. At its minimum, the global magnetic field strength fell to about 5% of its current value. For roughly 1,000 years, the planet had almost no shield. Solar and cosmic radiation reached the surface with almost nothing between it and the organisms living there. Neanderthal populations, already under pressure, declined sharply in this period. The precise connection is still being studied, but the timing is exact enough that researchers at the Norwegian Institute for Air Research published a paper in 2021 directly linking the excursion to Neanderthal extinction. 5% of the magnetic field for 1,000 years. The field has been weakening again. Right now. Since the 1800s, Earth's magnetic field has lost roughly 9% of its overall strength. The South Atlantic anomaly, a region of significantly weakened field over South America and the Southern Atlantic, has grown larger and deeper every decade. Satellites passing through it routinely experience electronic glitches. The European Space Agency's Swarm constellation has been monitoring it since 2013, and the data shows it is not stabilizing. Some researchers believe it may be a precursor to a geomagnetic excursion, not a full reversal, but a temporary weakening of the kind that coincided with Neanderthal extinction. Others say it is just normal variation, that the field does this sometimes, that it will recover. They might be right. But the question that keeps serious researchers awake at night is not whether this will happen again. It is whether it is already starting, and whether we would be able to tell the difference between the beginning of a crisis and just another quiet Tuesday. There is a concept in risk analysis called normalization of deviance. It describes what happens when a system operates for a long time without a catastrophic failure, and people gradually begin to treat warning signs as background noise. The shuttle engineers who approved the Challenger launch in below freezing temperatures had seen O-rings perform poorly in the cold before. Every time the shuttle flew anyway and came back safely, the risk felt more manageable. Not because it was, because nothing had gone wrong yet. We have done this with the sun, not because we are reckless. Because the sun is old and the civilization is young. We built everything we have, the grids, the satellites, the fiber optic arteries, during a period of relative solar calm. The last major geomagnetic storm to affect infrastructure at scale was the 1989 Quebec blackout, which knocked out the entire Hydro-Quebec power grid in 92 seconds and left 6 million people without power for 9 hours. That storm was a fraction of the Carrington event's intensity. We looked at it, took some notes, and kept building the same kinds of systems. The infrastructure protecting us from solar events today is marginally better than it was in 1989. Not orders of magnitude better, marginally. This is not a story about negligence. It is a story about timescales. Human beings are not built to take seriously the things that happen once every few hundred years. Our institutions are not built for it either. A government that protects against a solar superstorm is spending money to prevent something that will probably not happen during any single term in office. The incentives point the other way. They always do. But the ice cores do not care about incentives. They just record what happened. And what happened is this: a species much like us, living on this same planet, under this same star, found itself exposed to something the sky sent down without warning. It did not have power grids to lose. It did not have satellites to fry. What it had was thin shelter, stored food, and the slow catastrophe of a broken food chain. And it did not make it. We are different from Neanderthals in important ways. We are more adaptable. We build better tools. We can, in theory, look at the evidence and respond before the event rather than during it. We have the instruments to watch the sun in real time: SOHO, Stereo, the Parker Solar Probe, which has now flown closer to the sun than any object we have ever built, skimming through the outer corona and sending back data about what the near-solar environment actually looks like from inside it. We know more about the sun than any civilization in history has ever known. And we still have approximately 15 to 45 minutes of warning time between the detection of a major coronal mass ejection and its arrival at Earth. That is the window, 15 minutes on the low end, for hospital systems to switch to backup, for grid operators to manually disconnect the most vulnerable transformers, for satellite operators to put their hardware into safe mode, 15 minutes to begin protecting a civilization that took 10,000 years to build. The Parker Solar Probe has suggested that warning time could be extended by moving detection equipment to a point between Earth and the Sun, a location called the L1 Lagrange point, where we already have some instruments. Better instruments, positioned correctly, might give us an hour. Maybe more. That hour is not nothing. That hour is the difference between managed disconnection and cascading failure. But the hour requires investment. It requires someone deciding that a thing that has not happened yet is worth preparing for. It requires the kind of slow, unsexy, forward-looking work that civilizations do not do well under normal conditions. We are not in normal conditions, yet the magnetic field is weakening. Solar cycle 25, the current cycle, has already exceeded expert predictions for activity. In 2024, a series of X-class solar flares produced the strongest geomagnetic storm since 2003. The northern lights were visible from Arizona, from France, from the south of England. People took pictures and posted them online and called them beautiful. They were beautiful. They were also a reminder. The same physics that makes the sky glow in colors it should not is the physics that ends the power. The sun has been here for 4.6 billion years. It will be here for another 5 billion. We have been here for a fraction of a percent of that time, a thin layer of activity on a small rock in a quiet corner of an average galaxy. In all that time, the sun has not once considered whether we were ready. It has not needed to. We are the ones who have to be ready. And right now, at this moment, in this version of the world, we are not.